Hi, I'm Eunjin Kim and I'll be presenting this work on behalf of my collaborators. Our work focuses on continuous spatial-temporal video super resolution. It represents the videos as continuous functions via implicit neural representation. Therefore, given low-resolution, low-frame rate videos as input, it can generate high-resolution, high-frame rate videos with arbitrary upsampling scales. However, current CSVSR approaches still have limitations. First, they often rely on naive positional encoding, while positional encoding is widely used with INR to enhance representation power. Second, they rely on pre-trained optical flow networks for motion modeling, making them inefficient and computationally expensive. Lastly, to carry RGB value at a target time t, they perform recursive inference at each time step, which limits scalability. Furthermore, our works motivated from the video representation. Here, to generate high-resolution intermediate frames, the model needs to focus differently along each axis. In temporal axis, the model should predict smooth and inherent motion of video to generate continuous videos. By predicting smooth motion, the objects move smoothly and continuously, rather than in jerky manner. While in the spatial axis, models should capture high-frequency components to generate high-resolution frames. Based on these motivations, we propose axis-wide positional encoding for CSVSR task to generate intermediate high-resolution frames. For temporal axis, we use B-spline basis function. It is a well-established method for modeling smooth and continuous signals. Therefore, it is well suited for capturing the continuous nature of video motion where objects move smoothly and continuously. And for spatial axis, we use Fourier basis function. Fourier basis functions are well known for estimating dominant frequency components, helping INR network overcome spectral bias and better represent the objects. Therefore, it is well suited for capturing the fine details of input video frames. Based on these motivations, we propose novel framework called BF-STVSR. It represents video dynamics better with axis-wise signal basis positional encoding. Also, by eliminating the need for external optical flow supervision, we can train the model with simple process. Lastly, using input features directly without pre-trained networks enables efficient inference process. BF-STVSR starts with taking two low-resolution frames as input and extracts latent features. These are processed by the B-spline mapper, which represents latent features with B-spline representation. It predicts three components which are coefficient, knots, and dilation. By predicting various forms of B-spline basis functions, we can estimate smooth motion vector at the correct coordinate q. Furthermore, inspired by previous work local texture estimator, we represent special features with Fourier representation. It predicts two components which are frequency and corresponding amplitude. By predicting frequency components at correct coordinates, the model gets refined special features at the correct coordinate q. After that, the predicted motion vectors are used to warp the features, and the warp features are concatenated with other features and decoded to generate high-resolution intermediate frame. For training objective, prior works incorporate optical flow supervision during training. In contrast, our framework simplifies the equation while still achieving performance comparable to or even better than supervised method. For experiment, we evaluate our method with other baselines. We train BF-STVSR with scaling factor of 4 in spatial and 8 in temporal. We compare CSVSR baselines not only with in-distribution scaling factor, but also out-of-distribution scaling factor, which is not seen during training. Compared to others, BF-STVSR generalizes better to unseen scales. For qualitative results, BF-STVSR shows clear improvement in upsampling low-quality video input. Also, among CSVSR baselines, BF-STVSR provides the most visually appealing results without ghost effect. We compare the flops and inference time of the baselines. The evaluation is conducted with a spatial scale of 4 and varying temporal scales. Our model consistently achieves the lowest computational cost and fastest inference across all temporal resolutions. Also, we compare the performance with and without the pre-trained optical flow network across different combinations of our proposed mappers. As seen in the upper row, including the optical flow network with the proposed modules degrades performance. In contrast, as seen in the last 4 rows, directly using the proposed modules to extract spatial and temporal features improves performance across all cases. For summary, we propose BF-STVSR framework consisting of B-Spline mapper and Fourier mapper. And we eliminate optical flow supervision while keeping high performance. And our model achieves state-of-the-art results in diverse metrics. Thanks for watching, and please check our paper and website for more details.